All right, so let's keep going on this assignment. I will point out I'm doing all of these as if they're free response questions. Most likely these types of limits would be multiple choice. So if it's a multiple choice problem, unless you need to for yourself, you don't have to formally write out that both of these are zero or whatever. You can just recognize that in your head, infinity over infinity, and then get to it. But I'm just doing them just so you get in the habit, because if it is a part of a free response question, then we do need to show this to get credit for it. You would get partial credit for correctly doing L'Hopital's, but you wouldn't get full credit, and it's an easy point. You don't want to miss it, even though it's tedious. Okay, so anyway, so both of these limits are infinity. So I'm going to use L'Hopital's rule. So the original limit at infinity of x cubed over x plus 2 can equal the limit as x approaches infinity of 3x squared over 1. And that's 3 times infinity, which is just infinity. So this limit does not exist, and it's equal to infinity. All right, for my next one, this is not just equal to 1 by like something that we know, but I will say this: I don't necessarily need L'Hopital's on this, because remember, cosine is one of those graphs that we know, the first period from 0 to 2 pi looks like that. It just keeps going, and it fluctuates between 1 and -1. This will just keep going on. So this is any value between 1 and -1. That's sort of our max and min. But the denominator is going to keep growing. So it doesn't really matter what the top is. It's something small between -1 and 1. This is going to close it on 0. So I actually don't need L'Hopital's rule for this, or any real manipulation. Okay, 434. We've got, again, something between, this is the same thing. Sine is going to stay between -1 and +1. It's not going to exceed those values. And x minus pi is going to continue to grow to infinity. So this is also going to be 0. And we don't have any extra work to do. For 35, if I plug in infinity, this is getting to infinity over infinity. So let me show that. So the limit as x approaches infinity of ln x is equal to infinity. And infinity is also equal to the limit as x approaches infinity of x squared. And I guess I'm not cheating, but I'm sort of not writing all the work that I was before. So instead of rewriting the original, I've got space here to say, okay, so this limit originally is equal to the limit of the derivative of the top over the derivative of the bottom. So derivative of ln x is 1 over x. The derivative of x squared is 2x. You can simplify that if that helps you do the algebra. 1 over x divided by 2x is like 1 over x times 1 over 2x. So that's 1 over 2x squared. And this becomes 1 over infinity, which is 0. All right, so let's take a look at the next section. This says, part A says, describe the type of indeterminate form. So that means, we're going to do this informally. Is it 0 over 0, infinity over infinity, whatever? Evaluate the limit using L'Hopital's if necessary. Use a graphing utility to verify. So I left the graphing utility up here. All right. So if we plug in infinity, we get infinity times infinity. So that's infinity times infinity is not an indeterminate form. So we put that on our notes, like infinity divided by infinity is, because we don't, that's not always just 1, as we've discovered. Oops, I didn't spell this right. Not indeterminate. So infinity times infinity is infinity. So the answer to this limit of x times ln x as x approaches infinity is infinity. The limit does not exist. The graph is unbounded. And if I graph x times ln x, I can see, as I trace this, it's just going to keep growing. I think this note is for part C down here. So, yeah. So, all right, for this next one, let's plug in with direct substitution. x becomes infinity times the tangent of 1 over infinity. 1 over infinity is 0, and the tangent of 0 is 0. So 0 times infinity times 0 is indeterminate. I really can't spell today. Indeterminate. And so, yes, we do need some L'Hopital's for this. Remember, L'Hopital's is not going to work if it's in a product form like this. So I need to rewrite the problem so that it's a rational expression. So I can leave, my note over here was like, I tried to leave the x on top and put a change tangent to cotangent. Like multiply by tangent is the same as dividing by cotangent. I still get an indeterminate form, so it doesn't matter. So my first thought would be to leave the tangent alone. And then instead of multiplying by x, you can say divide by 1 over x, because dividing by the reciprocal of something is the same as multiplying by it, right? Now, this still gives me the limit as x approaches infinity of the tangent of 1 over x. That becomes tangent of 0, so that's 0. And that's the same as the limit as x approaches infinity of 1 over x. Both of those are 0, so I need L'Hopital's. So again, I'm going to, just in interest of time, I haven't written the original, but I'm going to say like, okay, this original is equal to the limit as x approaches infinity of the derivative of tangent is secant squared. And then chain rule, the derivative, excuse me, of 1 over x is negative 1 over x squared. And in the bottom, the derivative of 1 over x again is negative 1 over x squared. So that's nice because those cancel out. So try direct substitution again. This is now secant squared of 1 over infinity, which is 0. Now remember, cosine of 0 is 1. So secant of 0 is 1. So 1 squared is also 1. Check this graphically. If you graph x times tangent of 1 over x, you get this. And as we approach infinity, it does look like this is leveling out. If I hit trace on my calculator, the values should be approaching 1. In interest of time for the video, I'm not going to graph that again. All right, let's look at 49. So if we plug in 0, we get 0 to the 1 over 0. And remember, 1 over 0 is infinity. 0 to the infinity power is not indeterminate. The indeterminate forms, I really can't talk and spell this word. The indeterminate forms are 1 to the infinity, and what was it? Infinity to the 0. So 0 to the infinity, 0 to the 0 is indeterminate, but not 0 to the infinity. So 0 to the infinity is still just 0. The limit as x approaches 0 on the right of x to the 1 over x is equal to 0. We can see that here. Here's the graph. It does this weird thing here. I'm not quite sure what's happening back there. Something about domain, I'm sure. But as we approach x from the 0, we get right over here. All right, take a look at this one. So when I do infinity, I get 1 plus 1 over infinity to the infinity power. This is 1 plus 0. So this is 1 to the infinity. This is indeterminate. Now remember, this kind of looks like a compound interest formula, and it's e to the a b. So remember, this is one of the blink and be done ones. You can do this the long way with introducing a y and natural log and doing all of that. But if it looks kind of compound interesty, then your best guess is to say, oh yeah, that's probably supposed to be e to the ab. And what are a and b in this case? A is 1. B is the coefficient in front of, A is 1, the coefficient in front of the 1 over x. And then B is the coefficient in front of the exponent. So both of those are 1. So this is e to the 1 times 1, which is just e to the first. Again, if I graph this 1 plus 1 over x to the x, I get this graph. And if I were to trace this, I should be zeroing in on a value of e as I approach to the right. All right, let's see. Take a look at 66. Use a graphing utility to graph the function and find the required limit if it exists. So it looks like there's a limit that exists, right? It kind of looks like it's 0. So let's go through and find this. This is, now I kind of know ahead of time that it's going to be 0 because I think about function races. A cubic, as in the long run, as we approach infinity, will not grow as fast as an exponential. So in the end, the denominator will be much larger than the numerator. So it should be 0. I think of this as like bottom heavy. It should be 0, but we do have to show the work for that. So the limit as x approaches infinity of x cubed is infinity. And infinity is also equal to the limit as x approaches infinity of e to the 2x. So that means that we're going to use L'Hopital's. So I'm going to, again, in interest of time here, I'm almost out of it for my bell. I am going to just go ahead and do the derivatives. So the derivative of x cubed is 3x squared. Derivative of e to the 2x is 2e to the 2x. I still get infinity over infinity. So I'd have to say, okay, so now the limit as x approaches infinity of 3x squared is still infinity. And maybe you can see like, okay, we're going to have to keep doing this until we get down to a constant in the top. So yeah, so I'm going to show my work for this. But then I'm probably, to be honest, I'm going to stop showing that fully. So now I want to say, okay, do another round of L'Hopital's. What's the derivative of 3x squared? 6x. What's the derivative of 2e to the 2x? 4e to the 2x. Because of chain rule. Again, you're going to get, I'm just going to say L'Hopital stuff. You're going to get the same thing, infinity over infinity. So I would write it out formally. And then I'm going to say, let's do one more round. X approaches infinity. The limit of that is now equal to 6 over 8 e to the 2x, because chain rule again. Now plug infinity in and you have 6 over infinity, which is 0. So all of that work to say what I kind of knew it should be. If this is multiple choice, I'm not going to bother with any of that. I'm just going to say, oh, it's 0. But if I need to double check or if it's free response, I've got to do it the long way. All right, let's take a look at this. Oh, I left my answers up for these writing ones because I just wanted to kind of talk about them. There's not like a lot of work to show. So list the 6 indeterminate forms. Okay, did that. 0 over 0, infinity over infinity. When we get 0 times infinity and infinity minus infinity, these are the ones that we usually rewrite. And then we try to do L'Hopital's. And then when we have 1 to the infinity, those are the ones that we either need to introduce y and natural log, or if it looks like a compound interest type formula, then blank and be done, e to the ab. Infinity to the 0, I don't think we've seen too much of that, but again, we usually rewrite that, work on it, and then go from there. 68, state L'Hopital's rule. So it's basically saying if the limit, as we had this in our notes, if the limit as x approaches c of f of x over g of x is indeterminate, meaning one of these two, 0 over 0, infinity over infinity, then the limit as x approaches c of f of x over d of x is also equal to that same limit of f prime over g prime. All right, there are a lot of answers you could have for number 69, but it says find differentiable functions that satisfy the specified condition. So the limit as x approaches 5 of f has to be 0, and the same thing for g. So, okay, here's my f of x and here's my g of x that I thought of. What I was trying to come up to was what you're trying to get with those stipulations are like, you want to have a limit that comes out to 10, a limit that comes out to 0, and a limit that comes out to infinity when you divide them. So for each part, I changed f and g a little bit. So for f, I thought x squared minus 25 over x minus 5. When I simplify that, I'll be left with x plus 5. So that will give me the 5 plus 5, which is 10 that I need. For part B, if I want it to be 0, I need something bottom heavy. So I just kind of switched it up. I put the, I changed f and g and just redefined them and switched them. So again, you didn't have to have the same exact one. You didn't have to have the same f of x and g of x for all 3 parts. So I just switched them. This is bottom heavy, and now it would be 1, or it would be, oh no, wait, this would be 1/10. I didn't do that right, did I? We need to make this I need to change this. So it needs to be, hold on. That would have been 1/10 that limit that I had, not 0. So let me fix this. Okay, I can't just switch them. I want this to come out to be 1. I want it to be like I get 0 in the top. So maybe I get 5 minus 5 in the top. So I think I can just do this. So let's keep f of x as x minus 5, x plus 5. And let's just change g of x to x plus 5. There we go. I was probably not thinking or going too fast when I did my answer key. So the x plus 5s will cancel, and then when I plug in 5, I will get 5 minus 5, which is 0. All right, and then for part C, let's see if I did this one correctly. So now I have f of x is x minus 5, and I have g of x is, I just wanted it to be something cubic. I guess it could have been squared. That would have been fine. This could have simplified to just 1 over x minus 5. But either way, you're trying to get it to a point where it's 1 over 0, and then that becomes infinity. So I could have just made this squared as well. All right, and then for 70, find differentiable functions such that the limit at infinity of f is the same as g, and they're both infinity. And then when you subtract them, the limit of at infinity is 25. So I chose 2 quadratics. Individually, each of those right end behaviors is increasing to infinity. So they both have that limit. But if you subtract them, you get x squared minus x squared plus 25. So you're getting the limit as x approaches infinity of just 25, which is 25. Again, there are a lot of ways you could obtain the same thing. I just thought of quadratics at first. I guess lines would have been fine too. X and x minus 25. L'Hopital's rule is used incorrectly for these problems, so describe the error. So it looks like they just started L'Hopital's without actually checking. If you do direct substitution, if you plug 0 into this, you get e to the 0 minus 1, which is 0, and then you get e to the 0 on the bottom, which is 1. And so that's equal to 0. We didn't need L'Hopital's rule, excuse me, because we did not have an indeterminate form. Take a look at the next one. Again, they jumped right into L'Hopital's, and then they canceled this out and they canceled these out and just left this with like the limit of nothing. It should have been the limit of 1, I guess. But let's see, maybe L'Hopital's just didn't even apply. So if I plug in infinity, because remember, this is e to the negative x, so you're getting 1 over infinity, which is 0, and then you're getting 1 plus 1 over infinity, which is 1 plus 0. So this, again, is not indeterminate. It's 0 divided by 1, which is 0. Why don't I have these on here? Let's see. Maybe I haven't done these yet. Okay, so let's take a look at 108. It says, find the value of c that makes the function continuous at x equals 0. So, oh no, wait, I have done these, sorry. Okay, so find the value of c that makes the function continuous at 0. So think about continuity. Remember, the definition was that f of c, the function value of c, has to equal the limit as x approaches c of f of x for a function to be continuous. So I want to start with that. So I think I want to put my limit on the left because that's where I'm sure all of my work is going to be. So let's start with the limit. The limit as x approaches 0 of, let's use the non-c term, e to the x plus x to the 1 over x. That is supposed to equal f of 0. Okay, so f of 0 is the easy part. F of 0 is c, right? So we're supposed to come up with some value for c, and c is just going to be, what is the value of this limit? All right, so this does not look compound interesty to me, unfortunately, so we get to go through the whole thing. So let's introduce a y, and then natural log both sides. So this is the natural log of this expression. And I'm going to leave off the equals c part, so I'm ignoring this part for now. So, okay, so we have this. And then remember, we natural log so that we can bring the exponent down. So the natural log of y is equal to the limit as x approaches 0 of the natural log of e to the x plus x. And then instead of times 1 over x, I'm just going to say over x. All right, now let's think about plugging in 0. If we plug in 0, we get the natural log of e to the 0, 1, plus 0. The natural log of 1 is 0, and that'll be 0 here. So let me do this formally. So the limit as x approaches 0 of the natural log of e to the x plus x, that's 0. And 0 is also the limit as x approaches 0 of x. So now we can use L'Hopital's rule, which is to take the derivative of the top and the bottom. So the derivative of this natural log is 1 over the expression in the natural log times chain rule. The derivative of e to the x is e to the x. Derivative of x is plus 1. And then don't forget about down here, the derivative of x is just 1. If I plug 0 into this, I get natural log of y equals e to the 0 is 1. 1 plus 1 is 2. E to the 0 is 1. 1 plus 0 is 1. So I get that natural log of y equals 2. And then we're going to base e both sides, inverse operation. So y is equal to e squared. And remember, this entire equation was equal to c. So c is equal to e squared. All right, last example. Show that this expression is equal to 0 for any integer n greater than 0. So first off, I'm going to show that the limit as x approaches infinity of x to the n would be infinity. And the same would be true for the limit as x approaches infinity of e to the x. So we can do L'Hopital's rule that says the limit as x approaches infinity of the derivative is equal to this original one. So n times x to the n minus 1 over e to the x. It says show that this limit will equal 0. So I'm not going to do a bunch of rounds of this because if I keep going, I guess there are probably a few ways to explain this, but if I keep going, I'm just going to keep getting more n's, whatever. This doesn't have an ending point. So let's investigate here. N has to be greater than 0. So let's kind of work that out here. So let's say n is greater than or equal to 1 so that this exponent stays positive. So if that's true, then the numerator will become a constant. Like we're going to get if I keep doing L'Hopital's and n is something that's not negative, so say it's x cubed, it's x to the 4th, whatever. After several, I'm abbreviating, L'Hopital applications, the numerator will become a constant. Right? If we have something algebraic, if this is like x cubed, x squared, whatever, after a few rounds of derivatives, you're going to get some sort of constant up here over an e to the x. Over e to the x. So therefore, that limit as x approaches infinity of a constant over e to the x will equal 0. What if n is greater than 0, but it's a fraction? Because if that's the case, then when I do my derivatives, I'm going to be getting x's in the denominator. So if n is between 0 and 1, then I'm going to get the limit as x approaches infinity, x to the n times x to the n minus 1 over e to the x. And that simplifies because this will be n minus 1 will be less than 0. This will be a fraction minus 1 will be less than 0. So that will change this to the limit as x approaches infinity of the n will stay up here, but the x's will come down. Whatever, it'll be positive, but it'll be its fraction, e to the x. And so that means like this will be x to the 1/2. And so that will also be 0 because you'll have a constant over infinity. So yeah, in either case, you're going to get something that comes out to 0. It's always kind of hard to think abstractly like that. So I don't know. If you're having trouble with the ends, just think about actually plugging numbers in and the couple of different scenarios you can get. All right, that finishes up this video. This is a long assignment if we're really doing things formally. So yeah, good practice, but definitely a lot of work.